Right, perfect. Yeah, and Brad is sorry, everyone, that he couldn't make it today. He had an appointment that he had hoped would let up in time so that he could join us for the start of this, but he might be logging in just a little bit later. But if everybody is ready, Melanie, should we get started?
Sure.
Okay, great, perfect. Well, I'd like to welcome everybody here this afternoon to the Research and Practice Seminar. And I'd like to say a special thanks and introduce Professor Melanie Weil from Environmental Health for this presentation. We've been looking forward to this presentation actually for weeks, so I'm really excited to hear about your research. This is going to be really cool. And I'd just like to say that anybody attending this, you can feel free to unmute yourself at any point during the presentation so that you can ask questions, or you can drop them into the chat, whichever way you're most comfortable with. We like to kind of keep things informal here. So either is fine, but we'll also save some room for questions at the end of the presentation today. So with all that being said, I would like to hand the floor over to Melanie. Take it away.
Great. Well, thank you very much for that introduction. And yeah, I'm very comfortable with you just interrupting me. If things go into the chat box, I always say, put stuff into the chat box, and then I get distracted. So just blurt out. It's much easier. So I'm going to share my screen here. Hopefully it's going to work. Alrighty. Oh dear, cancel. Okay, can everybody see the slide? Display settings, swap. Can everyone?
That looks good. Yeah.
Okay, let me just get rid of this. Annotate, get my little, where is it? Spotlight. I want a pointer. I don't think that worked. All right, I don't have a pointer. I'll just use my mouse. Okay, so thank you again. I'm excited to talk about my research in boreal peatlands of Alberta, Canada. I've worked in these systems for quite some time, more than, I'm going to date myself here, but 25 years or so. And I have really great collaborators from Villanova University and University of Southern Illinois who we've worked together for quite some time to try and understand how these ecosystems function, and then also how they function in light of climate change and oil sands mining. Okay. So I thought I would start off with just a brief overview of what peatland ecosystems are. I'm sure not everyone is familiar with them. And then briefly talk about some of the ecosystem services that they provide, namely the fact that they store a large proportion of carbon on the surface of the earth. And then I'll talk a little bit about climate change impacts and oil sands mining in Alberta. And then I'll jump into the research that we've been doing over the last literally 20 years. And I will paint some really broad strokes because I would need probably the better part of a day to really in detail talk about the different projects that we've undertaken over the years. All right, so what are peatlands? Peatlands can be classified, at least in Northern Alberta and Canada in general, as bogs, poor fens, and rich fens. And this picture here of the bog, bogs are characterized in age as a function of the last fire. So in the background, you see a bog that is about 60 years old, and there's only one tree species. So black spruce is the only tree that you'll find in a bog. And then in the foreground here, you can see little bitty trees there. And that's because this site burned. And what you see in the foreground is about 30 years old. If we move down to poor fens, these fens they're all moss dominated, but in poor fens, you don't have any trees. So you just see mosses and some shrubs. And then in rich fens, it's also moss dominated. These are all peatlands, but in rich fens, you actually have more than one tree species. So maybe two, maybe three. These yellow trees here are larch. There's also bog birch and maybe one other tree. So today I'm primarily going to focus on bogs and poor fens. We've worked in rich fens, but the bulk of our work by far is in bogs and fens. So where do we find these peatlands? This graph here shows the surface area in square kilometers, and these are the 5 countries that contain more than 50,000 square kilometers of peat. And as you can see, Russia and Canada by far have the bulk of the world's peat. And thanks to Alaska, the United States is third. And then we have Finland and Sweden over here. And so the total peatland area is about 4 million square kilometers, and the boreal peatland area is 3.4 million square kilometers. And so by definition, the boreal peats dominate the landscape, with approximately 87% of the peatland area occurring in the Northern Hemisphere. So we work in the prairie provinces of Canada, primarily in Alberta, but we also have worked in Saskatchewan and Manitoba. And this graph was put together by Dale Vitt. He's my collaborator from Southern Illinois University. And this represents peatland cover. So you can see that the darker reds and purples and blacks is where we have the highest percent cover of peatlands. Most of the work that we do is in northern Alberta. And in that particular area, the peatland area can be as high as 70%, anywhere from 30 to 70%. Now, what's interesting about the prairie provinces of Alberta is that they contain 365,000 square kilometers of peat. Oops, and that's roughly 10% of the global total. And here you can see the current southern limit of peatlands in these 3 provinces. So there's a good chunk of peat in these 3 provinces alone. Now, if we look, this is a bird's eye view looking down on the Northern Hemisphere. You can see the boreal forest is outlined in green here. So we have Russia, Fenno-Scandinavia, and Canada and Alaska. And the boreal forest occupies a rather sizable chunk of the global forested area. It's approximately 30%. And while most of the boreal forest is underlain by mineral soil, a really large percentage, roughly a quarter, is occupied by peatlands. So when we tend to think about where on the surface of the earth do we find the most carbon, we tend to think about tropical areas, right? So there's lush rainforests in the Amazon, and there is a lot of carbon in the tropical rainforests, but peatlands actually have the largest store of carbon. So it's almost 2 times the amount of carbon per unit area as tropical forests. And so if we just take a second to step back and look at where we see the largest carbon stocks on the planet, with the darker reds representing the highest concentrations of carbon, of course, we see a band around the tropics, right? So here's the Amazon, and there is a lot of carbon there, but there's also a lot of carbon in the Northern Hemisphere in these peatlands. And the difference is that in tropical forest, most of the carbon is above ground. So when you think about those lush, different stories of trees and lush vegetation. And in peatlands, all of that carbon is underground. So that's the main difference. A lot of carbon in both ecosystem types, but in peatlands, all of that carbon most of it is below ground, while in the tropics, most of it is above ground. Okay, so this is a picture, another bird's eye view, if you will, looking down on a moss carpet. And this is sphagnum moss, and this top part is called the capitula. So if we look at net primary productivity, comparing that to sphagnum mosses versus tropics, So net primary productivity is the amount of carbon that plants take out of the atmosphere, and after respiration, what they convert to biomass. So if we look at NPP in the tropics, it can vary anywhere from 170 to 1700 grams of carbon per square meter per year. So these are typical units for NPP, or net primary productivity. And if we compare sphagnum, it's not going to win any awards, but it brackets what we see in the tropical forest, so anywhere from 100 to 900 grams of carbon per square meter per year. So this is even more impressive when you think about the fact that, you know, mosses are in the boreal zone. This is the Boreas, the Greek god of the north wind, and it's really cold there for a good chunk of the year. The mean annual temperature is anywhere between 1 to 3 degrees Celsius, although that's changing with climate change. And there are fewer than 120 days where the mean annual temperature is higher than 10 degrees Celsius, which is about 50 degrees Fahrenheit. And of course, that is also changing with climate. And if we compare the tropical zone, you know, the mean annual temperature is anywhere from 20 to 30 degrees Celsius. And those plants have the entire year to, you know, increase their NPP. And so I think it's just, you know, it speaks to the efficiency of sphagnum and how they've evolved with their climate to be as efficiently and productive as possible. Now, regardless of whether you're in a bog or a poor fen or a rich fen, the ground cover is moss dominated. So again, these are kind of, these top two pictures are bird's eye views looking down, and the top part is the capitula. Sometimes we call them pom-poms. And this is a side view of sphagnum growing, and you can see that I've shamelessly stolen this from the internet, and that's because my best picture is here on the bottom right, where you can, it's kind of a side view, and you can kind of get a sense of you know, the stem. So here we have the top, the capitula, and then these are the stems. And so mosses are non-vascular, which means they don't have any roots. And sphagnum growth is really interesting. So if this is a sphagnum stem in 2019, so typically it's about 2 centimeters of growth in a given year. And the previous year dies back. And so if we go to the following year, 2020, what was green and living in 2019 dies back, and the next year's growth shoots up from the top of the capitula. And that just keeps happening over and over again, year after year, so that over time you get this compaction of moss that if you were to take a core into the, you know, into the peat surface using very sophisticated sampling equipment, I might add, you know, a rubber mallet, a PVC pipe that's about 1/2 meter long, and a bread knife. Betty Crocker really is the best brand for this kind of work. And if you were to take that core and pull it out and lie it on its side, as you can see here, you can see the top 2 centimeters of growth, and then everything below it has died back. And you can see decomposition here. And then at the very bottom, you can see it's heavily decomposed, because you see that dark color, and this is still largely undecomposed. And so peatlands have accumulated this carbon on the landscape since the last glaciation. Okay. Let's see. There's one more thing I wanted to say, and I've forgotten it, so can't be that important, right? Okay, when we think about peatlands, I like to think about ecosystems in a framework of ecosystem services. And ecosystem services is a newish field where we try to put dollar values on the services that ecosystems provide in an attempt to not only value them, but to help in protecting them. So if you can make a case that by not chopping down a certain area of forest will allow New York City to save money on its drinking water, that money, you know, speaks volumes, right? Because the economics at the end of the day typically drive environmental decisions, although, you know, that's changing all the time. So when I think about peatlands, they really do fit this mold in the sense that they provide supporting services, regulating services, provisioning services, and also cultural services. So just to give you a few examples of that, Some provisioning services, Ireland is known for its peat. It has a lot of peat, not as much as Canada or Russia, but Ireland, used peat as a fossil fuel for a really long time. And of course, we can't deny the fact that Scotch whiskey is reliant on peat. So that's another provisioning service. But more importantly, in Alberta, First Nations peoples, so in the United States, we refer to Native Americans, and in Canada, it's First Nation peoples. And they rely on peatlands not only for habitat, but for caribou and moose as their meat, cloudberries, blueberries, and cranberries for part of their diet. So this is an important provisioning ecosystem service that oftentimes is overlooked, if you will. And so in addition to food production for First Nations people and fuel, it's also the case that primary production as a supporting service and climate regulation are really important in the sense that there's a lot of peat in Canada and Russia, and while peatlands only occupy a small percentage of the Earth's land surface, they store approximately 30% of the global soil carbon pool. So that's a pretty impressive estimate. So how you ask, how do they do this? Well, it's pretty simple through the process of photosynthesis. So this is a schematic that I drew up of a cross section, if you will, through a peatland. So we have a water table here. We have peat that's died back and is compacting. And then of course we have, the current year's growth. And just like any plants, mosses take CO2 out of the atmosphere through photosynthesis and convert that into biomass. And of course, mosses also respire. And then the mosses that have decomposed are also, sending CO2 and methane back to the atmosphere, but in much lower concentrations than what is converted into biomass thus far. And so these peatlands in northern Alberta have been on the landscape since the last glaciation, which is about 7,000 to 10,000 years ago. And depending on where you are, they can be anywhere from 2 to 9 meters thick. So these are really large peat deposits. And the reason that they've accumulated on the landscape is because photosynthesis exceeds decomposition. And that's been historically the case. Now, with climate change, temperatures are predicted to be the most volatile, if you will, in the Northern Hemisphere. So we expect to see the highest increases in temperature in these systems. And when that happens, when you have increased temperature, you have decreased moisture. So this water table, if it were to drop, all of the exposed peat above the water table is now subject to decomposition in an aerobic environment, which means with oxygen. And that means more CO2 and methane can be converted back to the atmosphere. So this is the concern, that with climate change, we will see these peatland ecosystems being converted from a net sink of atmospheric carbon to a net source. Okay. And lastly, but definitely not least, cultural services are, when you're trying to put dollar values on ecosystem services, these are the most difficult because they often are very subjective. We're talking about spiritual and aesthetics and recreational. And so I just happened to find mosses one of the most delightful plants on the planet, and I miss them terribly. Obviously, because of COVID, we weren't in the field last summer, and it's very unlikely we'll be there this summer. But there is nothing that brings me more delight than to step in a bog in fall when the mosses start to change color. And it's just so incredibly beautiful. And it's also very peaceful. I really just, there's just something about these ecosystems that I fell in love with, 25 years ago, and I'm still in love with them today. And if you're not convinced that mosses are pretty cool already, well, this is should seal the deal. This is a designer Fabian Felder, and she worked with a plant scientist and biochemist to harness moss as a source of energy. And so you can see here the mosses power a light, and they've also been able to power other things like radios and such. And Felder said that theoretically any plant could be used, but Felder believes that moss is beautiful and undervalued, and I could not agree more. Okay, any questions before I move on to oil sands mining?
I actually have a question. Can you walk on it, or are you gonna kill it if you step on it? Because it looks kind of like fragile almost.
Is this Grace asking the question?
Yeah. Hello.
Hi, Grace. That's a really good question. So there are a couple of things that factor into that. The age of the bog. So if you have a bog that is burned, you're going to go in up to your hips and maybe further. If it's a mature bog, you can walk on the hummocks. So there's a lot of topography where you have hummocks and then you have hollows. And it's always interesting to take undergrads up there the first time, teaching them how to walk through a bog. It's like, okay, don't step here, don't step there, and they're trying to figure it out. And so it really depends on you know, those factors, but also how often you return. So with our site, we build boardwalks, because if you were to walk day after day in the same path, you would kill the moss, and you would then actually cause the peat to collapse, and you would have standing water. So excellent question. But yeah, there are some serious bog walking skills that have to be attained before you attempt.
So Melanie, I have a question too. It's about the biology of sphagnum. This is Walt. I'm the science librarian and health librarian.
Yes.
Yeah. How does the sphagnum? It sounds like just the upper portion is still alive, but it remains contact with the dead portion that goes down into the depths. But how does sphagnum absorb nutrients? I know mosses don't have roots, they have rhizoids, but it seems like it would be cut off from its rhizoids. And I don't even know if rhizoids are nutrient absorption organs in mosses like roots are in other plants.
Yeah, that's a good question. So one of the amazing things about sphagnum, and especially fuscum and capillifolium, which are the dominant moss formers in boreal bogs, you can just see how tightly compacted they are. And as a result, they are able to retain their moisture pretty well. So they wick, because they don't have roots, it's like a big sponge. It just whisks the water up. And historically, these bogs are ombrotrophic, which means they're rain-fed. And so it was thought for the longest time that the only source of nutrients came from rain. And we know now through years of research that the mosses have a symbiotic relationship with nitrogen fixers. And it's not just cyanobacteria, it's also methane oxidizers, which was a really interesting finding. So this moss bacterial association has allowed sphagnum to basically gain the nitrogen that they need, because these systems are, historically located in places that have not received any nitrogen deposition from pollution. That answer your question?
Yeah, that's good. Thanks.
All righty. So moving on to the oil sands part of this. So we've been working in Alberta for years and years before we started to get interested in the impact of oil sands mining. And Alberta is sometimes referred to as the Texas of Canada. And that's because each one of these yellow dots has to do with some form of oil extraction. So as you can see, this is Alberta. To the left is British Columbia. And so there's a lot of oil in Canada. Within Alberta alone, there are 3 primary oil sands deposits: the Athabasca, which is the largest here, Peace River, and then Cold Lake. And if we look at a map of Alberta here, you can see these are the Fort McMurray, and this is the Athabasca oil sands, Cold Lake, and Peace River. How much oil do you ask? Well, in 2004, the United States imported more oil from Canada than it did from Saudi Arabia. In 2009, US oil imports from Canada surpassed those from the Persian Gulf. And as of 2019, 98% of our oil imports are from Canada, our friendly neighbors to the north. In the oil sands region alone, there's 1.7 trillion barrels of oil. However, economically recoverable is more like 178 billion, or roughly 10% of the total. And this is the third largest reserve in the world. So Canada has a lot of oil. And thankfully, because we are friendly neighbors, we have been relying on them for the bulk of our oil. Okay, just to give you a few more statistics, you can see here, so these are the deposits. The area of oil sands resources is approximately 140 plus or minus 1,000 square kilometers. The actual mineable area is a fraction of that, so 4,800. And then depending on your estimates, meaning depending on whether you get your numbers from the Canadian government versus industry, these numbers of total area being mined and tailing ponds can vary. And so just to give you an extent, or for comparison, Canada's total area is 10 million square kilometers, and the boreal forest is more than a quarter of that. So the boreal forest is really extensive, and as a result, there's a lot of oil there. Depending on what numbers you use, the total amount of area that has been mined is really a small percentage of the total. However, I will say when you're driving through the pit of despair, as my students like to call it, it looks like it's just a ginormous area. And I'll show some pictures in just a minute. So oil sand is, it's exactly what it's named for. It's oil mixed with a lot of sand. So it's really energy intensive. You have to use a lot of water to extract the sand from the oil. It's very energy intensive. It's, how much oil is pumped on a daily basis is driven by the price of oil globally. So you can imagine when the price of oil is cheap, it's not economically viable to be mining oil sands. If we look at the development of the oil sands area, so these are snapshots taken from Google Earth. So in 1984, it had a small footprint, if you will. In 1994, 10 years later, it expanded. In 2004, it expanded quite a lot. And that's about the time when we started getting interested in looking at the oil sands mining impacts on peatlands. In 2014, it reached its maximum. You can see the difference there. And if we swap out the 2014 picture for today, you can see that it hasn't changed much in the last 8 years or so. And the reason for that, again, as I was saying, is because of the price of oil. So if we look at the EROI of oil sands, so EROI is a ratio. It stands for energy returned over investment. And those ratios vary over time, right? So if we look at the first bar, this is the EROI of domestic oil in 1900. So high ratios mean that there's a lot of it, it's easy to extract, and it's economically viable. Low ratios mean that it's hard to extract, there's not very much of it, and it's not economically viable. So if you look at domestic oil in 1900, it was 100. In 1970, it was roughly half that, and you can see that it just decreases over time to the point where it's less than 12, it's less than 10 today, actually. So if you compare oil sands, or sometimes they're referred to as tar sands, depending on the ratio, I think the max was 4, but it's anywhere from 2 to 4. So this low EROI means that it's not economically viable or as viable as other sources, and it's difficult to extract. Okay. Another piece of the equation is nitrogen pollution. So these are the heavy haulers that remove the oil sands to the place where it's processed, And these are large, right? You can see there's a truck there for reference. And there are lots of these heavy haulers, they're called. And depending on, you know, how the price of oil is faring, they can run 24 hours a day, 7 days a week, what have you. One interesting fact is that they're diesel run. And so there's more nitrogen in the form of nitrogen oxide. So NOx is what we call them, from the trucks rather than the stacks. And this oil sands contains on average 6 times more nitrogen than conventional oil. So just the sheer movement of the oil sands with these heavy haulers is where most of the nitrogen pollution comes from, not from stack emissions down here. Okay, so this was the slide that I opened with, and you know, this is what pristine Alberta, you know, looked like before any significant oil sands mining impacts. And so in the background, you have upland islands and lakes, but then everything else is peatland. So there's some rich fens and poor fens here. And in the area where north of Fort McMurray, where the oil sand is being mined, those areas that were once pristine now look like this. So here we have, I believe this is Suncor and Syncrude in the back there. You can kind of see this yellow blob back there. That's actually a pile of sulfur that is removed with the scrubbers that they put on the stacks. Here you see the Athabasca River, which flows north, and the tailing ponds right along the sides of the river. And these stacks, even though they're outfitted with scrubbers, they release NOx and SOx. We refer to them as NOx and SOx. So in the back, Syncrude and Suncor, they're the two largest companies up there. And that sulfur is actually removed and it's just sitting there. And they're referred to as the sulfur pyramids of Alberta. And if you compare the sheer volume of the sulfur, so this is elemental sulfur just sitting on the landscape, to the Great Pyramid of Giza, by volume, there's more sulfur in Alberta than in the Great Pyramid of Giza. This is true. You can't make this stuff up. Okay, so why is this important about nitrogen? Well, if we look at nitrogen deposition across the globe, so I'm going to show you 3 different panels. The first is nitrogen deposition in 1860, then in the 1990s, and then what's projected for 2050. And here's the scale here. So the highest concentrations are in the orange, reds, and purples, and the lowest concentrations are in the blues and greens. And so if you just look over here at Alberta, you can see that it has some of the lowest deposition back in 1860. But that's also true in 1990. So you see a lot of nitrogen in Eastern North America, Europe, China, and India. And then projections for 2050 have much more, you know, in Central America and South America and Africa. And despite that, though, if you look at where Alberta sits, it's still in 2050 was projected to have concentrations less than 1. So 1 is extremely low, and it's really difficult to find areas across the globe that have N deposition of less than 1 kilogram per hectare per year. And so with oil sands mining, we're concerned that these ecosystems that have evolved over the last 7,000 to 10,000 years, in the absence of N deposition, how will that impact their functioning? Okay. So as I said earlier, I was going to paint a really broad brush because we've been working up there for quite some time. So I thought I would just give you a sense of the different questions that we asked and some of the results that we found for a few of these questions. But ultimately, we started out wondering if Alberta's peatlands actually do function as a net sink for atmospheric carbon. And the reason we asked that is because we set up a site to, you know, for a few years that we would monitor, and we come back and the site burned. And it's like, great, we just put in all that infrastructure. Now what do we do? Well, why don't we look at fire? So fire is what am I trying to say? Fire is a natural aspect of the landscape. There's a fire return interval of about 100 years. So no bog, I shouldn't talk in such absolutes. There are very few, if any, bogs that are older than 120 years. We also, because of climate change, wanted to look at drought stress and how that impacted carbon storage. More recently, we've been working with the Canadian government to develop indicator species. So, you know, that canary in the coal mine, if certain plants have concentrations of nitrogen and sulfur, can we use those for monitoring purposes? And then most recently, we've combined all of what we know about fire and nitrogen to look at the interactive effects of both, because we have fire on the landscape, we have oil sands mining, putting nitrogen into the landscape, and then we have climate change. So these are pretty massive projects that we've developed and were only able to carry out because we had so many wonderful technicians, master students, undergraduate workers. It really was a huge undertaking. And so the way that we measure carbon in peatlands is we go out and we build what we call collars and we insert them into the ground. And then we build chambers that are attached to an infrared gas analyzer that allows us to measure instantaneous carbon dioxide with time. And we do that at a variety of different sites that are aged at different ages since the last fire. We use shade cloths to determine the efficiency, the photosynthetic efficiency. And I don't know, there's probably, I want to say, at least a couple hundred of these collars all over the 365,000 square kilometers of peat. So we've been doing this for years. And some of the results that we published about a decade ago now suggested that as of 2009, peatlands are still functioning as a net sink for atmospheric carbon. However, with a change in the fire frequency, so I said the fire return interval is about 100 to 120 years. So if that is decreased to 61 years with no change in air temperature, that alone would convert the peatlands to a net source of carbon. So just changing the fire frequency would result in a net source of carbon. And an increase in non-winter air temperatures of 2 degrees Celsius would also decrease the regional carbon sink by about 37%. So you might have heard, with Greta Thunberg and a lot of other activists, we're trying to not get to 2 degrees Celsius warming. We're trying to keep it well below that. So again, this was in 2009, and we have ongoing studies up there. Well, we did until 2019. And we obviously haven't been able to go back, but these numbers are probably going to look a lot different for, 2019, 10 years later. Let's see how much time I have left, getting close. Okay, one other study was a synoptic survey. This was a lot of fun. So again, this is the oil sands mining footprint. And these yellow dots are places that we literally were dropped out of a helicopter over a span of 2 days. We had a crew of more than 20 people, and we sampled different plants, a bunch of different assessments. We took pore water. We cut down just one tree just to get the age. We looked for the biggest tree and we cut it down, and then we look at the rings, and that allows us to age the site. And the reason that we used a helicopter is because there are no roads that go to a lot of these bogs. And thus far, we've only picked sites that are road accessible. And so we wanted to get as close to the heart of the oil sands mining operations as we could, but we also wanted to sample away just to see the extent of how much the nitrogen and sulfur travels. And again, we had a fabulous crew. Kim Scott, who's at Villanova, is one of my biggest collaborators, and a bunch of graduate students, and there's another collaborator, Kel Weeder, in the back. And so we literally were dropped out of a helicopter, did our work, and came back and analyzed the data. I'm just going to show you data for just one species. This is Avernia mesomorpha. It's actually a lichen, not a moss. And the concentrations here for the amount of nitrogen in Avernia with the highest concentrations in the orange, red colors. And you can see it's superimposed on top of the footprint of the oil sands mining industry. And you can still see the parts, the little dots where we sampled. And so ultimately, the highest amount of nitrogen is found within close distances of those two main industries, Suncor and Syncrude. With as soon as you get I forget the exact how many kilometers away, but it's not far. You tend to see that footprint drop off, and that's not surprising because nitrogen and sulfur they have a short residence time, and they tend to fall out of the atmosphere pretty quickly, not too far away from the source. And we've seen that even more recently with the coronavirus. So these are data for China. So this is January 1st of 2020. And again, the dark oranges and reds indicate high nitrogen concentrations. And if you compare that just a month later, you can see how much of the air quality improved. You don't see those dark reds and yellows. So nitrogen tends to fall out of the atmosphere pretty quickly, and it also doesn't travel too far before it leaves that impact. Okay, so last but certainly not least, this is where we are still investigating today, looking at the interactive effects of fire and end deposition. So this picture here, so Grace, this is immediately after fire. In fact, if you look carefully, you can still see smoke coming off the landscape. So you can see that with the loss of the moss layer, if you step in certain areas, you tend to fall through. So it's a pretty dangerous walk through if you're not careful in a bog immediately after fire. But then this is a triptych that Kim Scott put together. So this is about 9 years after fire. You can see the trees are still burnt and about to fall over. And then here in the forefront is about 30 years after fire. In the background in this middle part is about 60 years post-fire. And then this is one of the oldest bogs that we had was about 100 years post-fire. And it's really super dense trees. They're really difficult to work in for reasons that are completely different for the recently burned bogs. And just briefly how we go about setting up these sites. We're kind of in the middle of nowhere. We don't have any running water. We don't have electricity. So we build boardwalks because we want to minimize our impact on the landscape. So this was kind of we have a video of this. So this is my collaborator, Dale Vitt, just about to put his hand on his head saying, what the what? The truck just dumped it. But we build boardwalks, you can see here, that go into the bog. This is actually a poor fen. And we build plots that are 10 meters by 5 meters or such. And to fertilize these plots with water, we had to get water delivered. So this was water that came from Fort McMurray. And my technician at the time, Jim Quinn, that's not him, this is the water guy. He had an engineering background, which was really helpful because we had to pump water more than a kilometer away. So we had these series of swimming pools, we called them, where a pump, so the nippy water guy would fill this with water, and then we'd have a series of pumps that would take the water from this pool. And if you haven't been to the site, it's kind of hard to realize this, but this is a hose taking water all the way down through the upland to the very beginning of the peatland. So the peatland is behind this shed here, where there was yet another pool where the water was dumped into here. And then another series of hoses went to a platform that we built in the middle of the bog and the fen with different nitrogen concentrations. So each one of these barrels, I forget how much water they held, but we had different concentrations of nitrogen, to which we then had people spray with a garden hose on the plots. So this is fertilization in the bog. You know it's a bog because you can see the trees, and this is in the fen. You know it's a fen because you don't see any trees in the forefront. Okay, there are so many different aspects of this this project that are ongoing. We published a good chunk of it, and there's a lot going on here. This is an aerial view of the site, so you can see here's the platform where the barrels of water were. This is the series of boardwalks that went all the way to from the fen to the bog, and then our plots. And essentially, we know that, and this was to simulate oil sands nitrogen, right? So we added nitrate and ammonia, and it led to a series of different results. But primarily the biggest result is that it allowed the shrubs to gain that nitrogen, and that leads to the shrubs then shading out the mosses. So when the mosses become shaded, they tend not to grow, and that could lead to a net a decrease in the net sink function is compromised. And we have like visual. I couldn't come up with a picture, not that I couldn't come up with it, I couldn't find it, where it's just to the naked eye, you can see the 25 kilogram treatment, and the mosses, the shrubs have really taken over that plot. All right, so as I said, again, this would not at all be possible without funding, of course, but with the huge crew that we've had over the years. And most importantly, I'll focus your attention here. Cal Weeder, my collaborator, and Kim Scott from Villanova University. That's me, and that's Dale Vitt from University of Southern Illinois. And with that, I will take questions.
Melanie, I have a question about the groundwater chemistry. Isn't it different between bogs and fens? And then how does that affect the whole system that you're looking at?
That's a really good question. Yes, it does differ. So bogs are ambrotrophic, so they have a raised surface, and all of most of their nutrients come in from, well, aside from nitrogen, all of their nutrients come from rain and other precipitation deposition. The groundwater is so far beneath the surface of a bog that the mosses at the top are unaffected. Actually, I have a slide, but I know we're almost out of time too. Whereas fens have groundwater relatively close to the surface. So they tend to have slightly higher, if it's a poor fen, slightly higher concentrations of nitrate and ammonium, but very slight. If it's a rich fen, then generally they have much higher concentrations of nutrients than compared to poor fens and bogs. So for this study, we worked in poor fens and bogs where the chemistry is pretty similar to the poor water. The poor water is pretty similar between the two, sorry.
I don't know, like, if it doesn't actually matter, but what happened, like, what happens when you guys aren't there? Like, does everything just stop, or like where, like, what's going on there now? Like, are your things still set up, or like, is it still collecting any information?
That's a really good question. I know, I'm so sad. So we have weather stations out there that are solar powered. Those batteries are probably dead, so we won't have any of those data. All of our infrastructure is there. It's probably buried because the mosses, you know, every year we put in these wires to measure growth, and they're only about, I don't know, 10 inches, but only like an inch or so is above the surface. So those are definitely buried, which will make it difficult to find those. The boardwalks tend to, you know, decompose over time because we don't want to get treated lumber for obvious reasons. And the bears really like plastic. So all of those frames that I showed you, the collar part, we now, instead of those square chambers, we use plastic buckets from Home Depot. and those are probably all chewed on. We have resin tubes out there to measure end deposition. There are PVC funnels. So yeah, they really like to chomp on plastic. So and you know, we left there. We always have a final trip in October, and we left there in October of 2019, not expecting COVID to happen. Had we anticipated that, we would have removed the more expensive pieces of equipment. And now, yeah, so this will be the second summer. Canada's having a surge in COVID, so I can't imagine that we'll be able to go. But yeah, I miss it.
Melanie, I have a quick question. What would you recommend people do that want to speak out against, you know, the degradation of these beautiful natural environments? I also have to say, I had no idea that mosses change color in the fall. That was really beautiful. That was so cool.
Well, you know, I guess immediately things that people can think about are to take a stance against the pipeline, the Keystone pipeline. You know, that has a huge impact on the delivery of the oil. But, you know, I don't know. I sometimes I have to remove myself from the, you know, my passion for the system itself, just because it exists and I find it beautiful. And you know, I'm always trying to sell it in that ecosystem services with, you know, carbon storage. But, you know, really it's what's happening globally. Temperatures are increasing, CO2 is increasing, and those, you know, have synergistic effects on these, especially in the Northern Hemisphere. So it's really a wide range of things that need to happen. We need to have government subsidize renewable energy. We need to move away from, you know, the traditional fossil fuels, and especially the unconventional ones like oil sands. You know, it's, yeah, I'm probably preaching to the choir, but.
Never hurts to reiterate these things. And but I understand how hard it is, you know, when there's a landscape that you know, sort of fall in love with like that, you know, it's, and you don't understand why everybody can't just get on board, you know, sometimes to just to save it for the sake of its, you know, its intrinsic value. You know, I'm from Florida, so I have like a special place in my heart for the Everglades, you know, which is totally different, but I kind of have the same concerns where I get worried about global warming and climate change and, you know, the rising seas and what's going to happen, you know, to that landscape. So it's like, it's both a global issue, but then like you do have like a little special place in your heart, you know, mourning the loss of some of these beautiful places on the planet.
Yeah.
I don't know if we have time, but that kind of leads to my question is, Melanie, how did you get involved with the situation in Alberta? There's the researchers in Villanova and Westchester. You know, it's how did you all get connected with?
Well, very, very quickly, I got my undergraduate degree at Villanova, and I took an ecology course with Kel Weeder, who worked with peatlands, and I got hooked. And then I did my master's degree at Villanova with Cal Weeder, and then I went to the University of Notre Dame to work with Scott Bridgham, who's also a peatland ecologist. And during my PhD, I was working in Alberta, so that's where I met Dale Vitt, because he was a faculty member at the University of Alberta at the time. And he's a bryologist, and man, it's a lost art what he has. He can identify mosses like no one I've ever met. And then I kind of switched gears for my postdoc. I went to look at carbon and methane fluxes in rainforests in Hawaii. I know, poor me. But after that experience, I decided that my heart was truly with peatlands, and I've been working with them ever since.
Good. I can understand.
Well, thanks again, Melanie. That was
Thank you.
that was really fantastic. Thanks for sharing all that.
Sure, anytime.
Yeah.
Thank you for having me. And yeah, I'm really excited. I was hired in January 2020, so I'm really excited to be part of Westchester.
Did you replace Mara or Chuck?
Chuck,
Yeah.
I mean, not that he's replaceable, but
Well, yeah, but that faculty line.
that faculty line.
Yeah.
Yeah.
Awesome.
Well, glad to have you.
Yeah, thank you.
Yeah, welcome.
I look forward to talking some more. I'm a paleobotanist, actually.
Oh, okay.
And
Yeah, we should
but
get
yeah,
together.
a bunch of my mentors worked in peatlands through time.
Oh, wow.
Yeah, carboniferous peatlands.
Cool. Yeah. So my master's degree, I actually looked at historical rates of heavy metal deposition in then Czechoslovakia. By the time I graduated, it was the Czech Republic. And because peat accumulates over time, it preserves the record of deposition of heavy metals because of the chemistry of the peat itself. It gloms onto those positively charged elements. And so that was really fun, using peat as an archival substrate.
Oh, it is an archive. Yeah. And speaking of which, has the library been good to you? Because I'm your person to contact if you need things.
The library has been wonderful.
Okay, good.
All righty, well,
Wow.
I guess, I mean, I'm happy to stick around. I'm not teaching anything this afternoon, so.
Okay, I have one more question for you. Was looking forward to meeting you in person on the Chester Ridley Crum Watersheds Association stream cleanup. You were on the list for the site where I was.
I know, I'm so sorry. So what happened was I was part of a live staking operation the Saturday before that, and it got canceled and it was moved to the same Saturday that you were doing the restoration. So then I had to choose, and because I was actually providing some of the live stakes, I thought, well, yeah, so that's where I went.
I figured it had to be something like that.
Yeah, too many live staking stream restoration projects, but it's all good. So
yeah,
yeah,
well, we do that every year.
Okay, yeah, I'm part of a few other. My husband teaches high school at Henderson High School, and he does a stream cleanup with his environmental club. They do, I forget what branch of the Brandywine, but it's, yeah, anyway, they do that a couple times a year.
Is that Taylor Run? Because that goes close.
Probably. It's
Henderson's actually in the Goose Creek watershed.
Yeah, but they go and get the canoes from Northbrook, so I'm not sure what.
Yeah,
so it's on the Brandywine.
That's in the Brandywine. Yeah, gotcha.
But I'm also excited to be here at Westchester because I was hired to teach sustainability courses. So I teach a course in environmental sustainability, and I also teach global climate change, and I also teach environmental regulations, which not my favorite, but
but necessary.
but I should know. So I know when they.
That's awesome. I've been part of the Sustainability Council, Environmental Council for over 20 years now.
Oh, that's great.
Yeah.
I would like to be more engaged with Westchesters. I started out being really engaged, and then I was asked to serve as the chair of West Goshen Township's Sustainability Advisory Committee, which was just formed last September. And that has taken a lot of my time, sadly.
Oh,
I mean,
so what municipality